In this example, we're going to eliminate the parameter to find a Cartesian representation of this following curve. And what I like to notice is we have x fully in terms of, in terms of one trig function, that trig function being a cosine of t, and y is equal to another trig function, sine of 2 minus t. There is one cosine with the x equation, one sine with the y equation. We're actually going to be able to use a trig identity to really help us out here. And that trig identity is going to be none other than the Pythagorean identity. Sine squared plus cosine squared equals 1. And the idea is we're going to take our x equation, we're basically going to solve it for cosine, and then we're going to plug that into the cosine term in the Pythagorean identity. Similarly, we'll take our y equation, we'll solve it in terms of sine, in terms of all the y stuff, and then we'll plug that into our Pythagorean identity. So the first thing we need to do is take our parametric curve, our coordinate functions, and solve them in terms of the trig functions that they have. So we'll start with x. We have x is equal to 2 cosine of t plus 3. So we can subtract 3 from both sides. To get x minus 3 is 2 cosine of t. And finally, we can divide both sides by 2 to get x minus 3 all over 2 is equal to cosine of t. So now we have a relationship between cosine and our coordinate x. We can do a very similar process to get sine in terms of y. So we have y is equal to sine of t minus 2. And then solving for sine, we just add 2 to both sides. So we have y plus 2 is equal to sine of t. So now we have sine in terms of the coordinate y. The next thing we'll do is take our Pythagorean identity and then substitute those values of sine and cosine into it. So we have sine squared of t plus cosine squared of t is equal to 1. Maybe an easier way for us to see how this substitution will work is we could rewrite this as the quantity of sine of t, that quantity squared, plus quantity cosine of t, and square that, and that equals 1. So you can see now we'll take what we have for cosine, which is that x minus 3. We'll be able to plug it directly into that parentheses for cosine of t, and we can take y plus 2 for sine, and then we can plug that directly into those parentheses for the sine of t. So let's make that substitution next. So sine was y plus 2. So we take y plus 2, put it in for sine, square it, and now we add to it what we have for cosine, which is the x minus 3 all over 2. And we can square that, and that quantity altogether equals 1. So we've effectively, at this point, eliminated the parameter from that parametric curve, and we have a Cartesian representation of it, a relationship between our x and our y. You may notice one other thing. The Cartesian equation that we have actually describes an ellipse. So if we do a quick aside for a moment and just remember things about ellipses, so let's note some facts about ellipse. So if we have a general equation of ellipse, we could write it as x minus x naught squared all over, let's say, a squared plus y minus y naught all over b squared equals 1. So some facts about this type of an ellipse. Number 1, this is centered at the point x0, y0. The second fact about this type of an ellipse, it has a semi-major axis of A or B, and a semi-minor axis of either A or B. Basically, the semi-major axis will be whichever is larger, A or B, and the semi-minor axis will be whichever is smaller between A and B. So what you can note, though, is it's A or B as a semi-major, semi-minor axes when we have in those denominators terms that are squared. So if we look at our ellipse up above, I'm just going to rewrite it as x minus 3, that quantity squared, all over 2 squared plus y plus 2, that quantity squared, all over 1 squared. And that equals 1. And we can write the x plus 2 all over 1 squared, even though we don't have anything in that denominator up above, because 1 squared is just 1. So it doesn't change that term whatsoever. So if we note a couple things about our ellipse, the first thing is that it's centered at the point 3 comma minus 2. The 3 because we have x of minus 3, just like we have up above. We subtract our point that we're centering at, but we have a minus 2 because instead of having a y minus, we have a y plus. So we need to have that extra minus sign in front of that point. The second thing that we can note is we know what a and b are. A is equal to 2, and b is equal to 1. So we have a semi-major axis of 2, because in this case, a is larger than b. And we have a semi-minor axis of 1. In this case, that semi-minor axis is b, associated with the y. So basically what we'll have is a more elongated ellipse horizontally than a tall ellipse vertically. So let's go ahead and try to plot the ellipse that we have. So let's quickly make a sketch here. We know this is centered at the point 3 comma minus 2. So let's go ahead and do that. So 3, 1, 2, 3, minus 2. There's the point in which we're centered. And now we're told we have a semi-major axis of 2. So this ellipse will move in the horizontal direction, a length of 2 each way. Whereas vertically, we have a semi-minor axis of 1. So it's only going to go up and down from that center point, 1. So let me try to draw an ellipse. So this is basically a plot of what our Cartesian representation looks like for that original parametric curve.